Hello and welcome to this next part of our series on UV-vis absorption spectroscopy. Last time we talked about conjugation and its effects on a system and how that can affect the absorption of different wavelengths. We saw that with an increase in the amount of conjugation or the increase in the conjugated size, we saw that the lambda max shifted to ever longer wavelengths, lower energies, because the energy differences between the highest occupied molecular orbital and the lowest unoccupied molecular orbital were decreased. And so they became much smaller. And what we had was this idea that increasing conjugation reduces energy, increases the wavelength, and so we get redder and redder colors for our compounds. So today we're going to be talking about the Woodward-Fieser rules, inorganic species, and charge transfer processes in analytical chemistry. And in the subsequent sessions, we'll start to talk about the uses of UV-vis absorption spectroscopy in analytical chemistry. So the effects of conjugation, as a recap, we saw that as we increase the size of the conjugated system, for example, whenever we have ethylene, there is no conjugated system here, even though there is a double bond, because there is only one double bond. In the case of butadiene, we now have a conjugated system because we have a double bond separated by only one single bond, followed by another double bond. So two double bonds separated by one single bond. This is in fact buta-1,3-diene. Then we have hexa-1,3,5-triene. So they are all in a conjugated system. They are all interconnected because the electron density can be shared along the whole length of this molecule. And then octatetraene has four different double bonds. They're again all separated by a single bond, and that means that they are going to be conjugated. And you can see as we increase the size of these, so we go from 1 to 2 to 3 to 4. Well, actually, this is not conjugated, but we go from one double bond to 2 in a conjugated system, 3 in a conjugated system, to 4 in a conjugated system. We see that the difference between this, which is the highest occupied molecular orbital, the HOMO, the energy of those increases, but the energy of the LUMO, the lowest unoccupied molecular orbital, decreases, so that we go to lower energy and longer wavelengths. So UV conformers and conjugation. So we saw this the last time where we had this idea of S-cis and S-trans. We had the S-cis conformer having a higher potential energy than the S-trans, which meant that these transitions happened at shorter wavelengths, which were higher in energy. So you can see here the cis has a lower wavelength, so a shorter wavelength, which means that it has higher energy. Remember, going back to Planck's relationship. Whereas the trans, it is more stable. It has a lower potential energy. And what we see is that the transitions shift to longer wavelengths, and we end up with a rather nice decrease in energy between the HOMO and LUMO. So the HOMO electrons have less of a jump to the LUMO. Lower energy means longer wavelengths. And so the S-cis conformer has higher potential energy than the S-trans. You can see here the effect of the different geometries and conformers on the wavelength that they absorb. So you can see here that more conjugation, longer wavelength. You can see here that both of these have 3 double bonds, only this is linear and this is cyclic, and that affects the wavelength. You can see that in benzene, the energy is slightly higher than in this linear triene. So UV absorption by organic species, as a little recap. So most absorption spectroscopy of organic species happens above 190 nanometers. Because remember, below this, we're kind of in the vacuum UV region, and that is usually something like an S to S transition, which is often going to just destroy the molecule, because what happens is that the electrons which are involved in bonding, they are separated from each other, as we saw in the previous sessions, and it destroys the bond and ultimately destroys the molecule. So we have typically, these are the transitions which we can view, which is the N non-bonding to the pi star antibonding, or pi to pi star antibonding. So this must contain an unsaturated functional group, and these unsaturated functional groups are called chromophores. Oftentimes, chromophores are not actually in themselves UV visible active, but when they are added to a system which is, they can often affect the wavelength by introducing more electrons in the case of things like sulfurs, like thiols, and hydroxyl groups have oxygens with lone pairs, and so on. Those can be added into any conjugated system, and that can change the wavelengths which are absorbed. These are typically broad spectra due to the superposition of electronic and vibrational transitions. There are a great many different transitions possible, a great many different energy levels, and these all kind of overlap. And so what ends up happening is that we don't see individual peaks anymore, rather we see broad continuum of wavelengths which are absorbed. The conjugation usually causes a shift of the lambda maximum, the maximum wavelength, to longer wavelengths. Longer wavelengths are going to be lower in energy. Higher wavelengths are going to be, shorter wavelengths are higher in energy. Remember, this is all related back to Planck's relationship that we talked about before. Saturated organic compounds with oxygens, sulfurs, nitrogens, or halogen atoms can be excited by radiation from 170 to 250 nanometers due to non-bonded atoms. So we can see here the absorption maxima, 255 nanometers for the benzene, and you can see that shifts to longer wavelengths as we increase the number of rings here. The number of rings increasing also increases the size of the conjugated system, which is going to cause a decrease in the energy difference between the HOMO and the LUMO. And so we end up seeing this shift towards ever longer wavelengths and lower energies. So the Woodward-Fieser rules. So the Woodward and Fieser formed extensive studies of terpene and steroidal alkenes and noted similar substituents and structural features would predictably lead to an empirical prediction of the wavelength for the lowest energy pi to pi star electronic transition. So what does this mean? It means that based on the structure of a molecule, they would be able to predict the pi to pi star electronic transitions wavelength. So if it had a certain number of double bonds, or it had like a methyl group attached, or it had some other structural feature, based on that structural feature, they could somehow determine the wavelength that it would absorb. So for example, the Woodward-Fieser rules for dienes. So the rules begin with a base value for lambda max of the chromophore being observed. So it depends on the structure initially. So in the acyclic butadiene, it starts at 217 nanometers as the basic absorbance wavelength. And then if we add other things like methyl groups and so on, that will affect the wavelength and will change it, but by a relatively predictable amount. So here are some tables of the rules. So for example, if a structural feature is like, for example, a heteroannular diene, what does that mean? It means if we have two fused rings and we have the double bonds, one in each ring like this. So it's a conjugated system here, but the two double bonds are in different rings of, so this is one ring and this is one ring. The double bonds are in different rings, but they are in fact conjugated here. There's only a single bond here. So it looks like they're not conjugated because they're in different rings, but actually they're conjugated. So that would have a lambda max of 214, after which we would add certain increments based on the different groups. So for example, if we have a double bond extending conjugation, so say for example, we had another double bond here, we would add 30 to the lambda max. So it would go from 214 to 214 plus 30, which would be 244, for example. If we have an acyclic diene like our butadiene that we saw on the previous slide, we start off with 217 nanometers as our base wavelength. And then if we have a homoannular diene, such as this, where we have a system of rings, maybe even just one ring, but inside of that one ring are both of our double bonds, then we have what is called a homoannular diene when we have two double bonds here. So this is diene because it has got two double bonds here, and it's conjugated because they're separated by only one single bond here. Now it's called homoannular because it is within one ring. This is called heteroannular because the double bonds in the conjugated system are in different rings. So hetero means different, homo means the same. So here we have our homoannular diene. So the increments change based on what is being added or taken away. So double bond extending conjugation, as I've said, if we add another double bond to our system, we add plus 30. We can do this for a great many number of times. Alkyl substituents are ring residues. So like, for example, the ring residues around here and around here, just these alkyl parts, just simple hydrocarbon parts. Those all change the wavelength. Could also be methyl groups appended to the conjugated system, like here and here. Exocyclic double bond, so a double bond somewhere else outside of the ring. Acetate group, so an acetate group, ether functional group, thioether group, so on bromines, chlorides, secondary amine group, and what have you. So let's do some examples of how we might calculate these things. So if we have isoprene, isoprene has is an acyclic diene. So you can see it's acyclic because there's no circle, there's no cycle, there's no like ring shape. So the acyclic diene starts off with a structural wavelength of 217 nanometers. Then this 217 nanometers is appended by one alkyl substituent. So it has got one methyl group here. And so that is number one. So we labeled it number one. So that will be plus 5. So we would expect to see a wavelength of around about 222 nanometers. The experimental wavelength for isoprene is 220 nanometers. So it's off by about 2 nanometers, but that's still really very close considering how just how close these are together. Like, I mean, this was just an empirical rule sort of estimate. And then we have this experimental value very close. So you can see these rules have some merit. Here we have another one. This is an example of a heteroannular diene. So what we have here is the conjugated system here and here, but we have on it alkyl substituents 4. So we have 1 here, we have 2 here, we have 3 here, and we have 4 here. Now they're all attached to this conjugated system, which is here. So it's going to be 214 for our heteroannular diene. So 214 from our table, plus an alkyl substituent, of which there are 4, is plus 20. So that gives us 234 nanometers. Inorganic species are also capable of absorbing UV light. So this is because they have, they don't have like a conjugated system per se, but what they do have is they have a lot of orbitals, which are quite close in energy. And those energies often fall within the boundaries of the UV-vis system. So what can happen is that they can absorb energies of a certain wavelength that's in the visible region, and we can see them as a certain color. And so this is part of the reason why a lot of inorganic solutions are colored, like the copper sulfate is a great example. That's a blue color. We can have others, pardon me, like iron oxide, which gives a wonderful, vibrant red-orange color. And there are many others available. Potassium dichromate, that gives us a purple color. And these are all because of the energy gaps between the HOMO and the LUMO of the different metal ions involved. So transition metals are often colored because they absorb broad bands of visible radiation. Transitions between filled and unfilled d orbitals are the cause of this. So these are our HOMO and LUMO within the system. We have, for example, a transition between the LUMO, or sorry, the HOMO, which is usually a d orbital, and another d orbital, which is going to be the LUMO. And that transition has often a wavelength associated with it. You can see over here different wavelengths that are associated. We'll talk about those in a moment. And the absorption maximum depends on the position in the periodic table. So which element it is, how many electrons it has, its oxidation state, and its bonded ligands. So there are a number of things which affect the transition and the position of this wavelength. Oftentimes, we've talked a little bit about this whenever we were going over some complexes in previous sessions, where a metal ion can have attached to it certain other atoms and can have other molecules attached to it. This is going back probably to some of your early analytical chemistry courses. So here we have different wavelengths. So we have a nickel 2+, we have a dichromate here, we have a copper 2+, and we have a cobalt 2+, and we can see the different wavelengths that they absorb. So this one absorbs around about 400 nanometers, so it's going to be like a kind of a greenish, bluish color. The nickel 2+, the dichromate is going to be like a kind of a very dark color at this low sort of wavelength here, around about 390, 370, something like that. Copper then absorbs here in a broad continuum near the edge of the visible region, so it's going to be a very dark red color. And then the cobalt here in the middle, around about 500, it's going to be probably quite a light blue color. So copper 2 sulfate, here is its color. So it's blue because it's absorbing the red light here at the end of the wavelength. So it's reflecting all the blue light. So it's a blue-like color. And then we have others like nickel 2 chloride. It's going to be green because of the wavelengths which it is reflecting and not absorbing. And you see these colors are caused by the transitions between the unfilled orbitals and the filled orbitals. So in the previous examples, we were looking kind of mostly at molecular orbitals. Here, we're looking at atomic orbitals. So in conjugated systems, we were dealing with molecular orbitals, which were filled or they were half filled. And then we had like these molecular orbitals were created because of the bonds between the carbon atoms. They were generally sort of say half filled or unfilled. Usually the conjugated systems had electrons in the HOMO, which would be excited via the absorption of the UV-vis radiation from the ground to the excited state. And then in this excited state, this transition would have some sort of wavelength associated with it, and that wavelength then would be very heavily influenced by the size of the conjugated system. As we saw in the Woodward-Fieser rules, it can even be predicted pretty accurately. Then in the case of the d orbitals, these are atomic orbitals. So most of these species, like the nickel, the copper, the cobalt, they're all individual molecular species in solution, and they all kind of absorb the wavelength, which is associated between the excitation of an electron from the ground state of that particular atom to the excited state, or well, that ion as it happens to be. So UV absorption by inorganic species. So lanthanide bands are usually narrow because the f orbitals are shielded by higher quantum number orbitals. So lanthanide, so we saw here the D block a number of reasonably sharp peaks, but they're still pretty broad. I mean, look at cobalt, copper. These are well, they're definitely peaks, but they're pretty broad, especially when we compare them to the lanthanides or the F blocks. So the processes are kind of similar here. They're individual ions in solution. They're absorbing to have an excitation. In lanthanides, it's F orbitals. In transition metals, it's D orbitals. What we have is a transition from the HOMO to the LUMO. In the case of the lanthanides, the process is similar. It's atomic orbital to atomic orbital, from atomic highest occupied molecular orbital, so atomic HOMO, to atomic lowest unoccupied molecular orbital, so atomic LUMO. We have pretty substantial excitation and what have you. Absorption because of that excitation. But in the case of lanthanides, the bands are usually narrow or quite sharp because the f orbitals are shielded by higher quantum number orbitals. So inorganic ions containing mostly nitrogen, oxygen, and sulfur also absorb UV radiation. So for example, these are inorganic anions, so they're not organic anymore. So we've got nitrate, we've got nitrite, we've got carbonate, we've got thiocarbonate, we've got nitride, and we've got carbon trisulfide. So these ions can also absorb, and like for example, here is the nitrate absorption. So you can see here that the nitrate absorption in water has this absorbance here. You can see it's got a pretty sharp peak, a bunch of different other things, some of which may be noise, some of which may be peaks and transitions, vibrational and otherwise. And then over here we have the europium and the so here we have the erbium 3+. You can see it's rather sharp peaks here and here. And then we have the praseodymium 3+ as well. It's got really sharp peaks, especially when we compare it to the broad peaks over here. So you can kind of see then in the difference from those F block or lanthanide materials, just like how kind of broad these peaks are in comparison. And then we have over here the erbium and the praseodymium ions. They're just like these sharp lines because of like the shielding that these orbitals undergo from the higher quantum number orbitals. So that's D block, F block, and inorganic ions can all absorb UV radiation. Here's some more absorptions by inorganics. So for the first and second transition metal series, the absorption process results from the transitions of 3D and 4D electrons. The bands are often broad here. The position of the maxima are strongly influenced by the chemical environment, and the metal forms a complex with other stuff called ligands. The presence of the ligands splits the d orbital energies. So if the solution absorbs the red region of the spectrum, it will appear blue-green. And if it absorbs the blue-green, it will appear to be red. And so these absorbances, as always, as I keep reiterating, are going to be kind of related to the energy difference between this HOMO and LUMO. This HOMO-LUMO gap is going to influence just what energies are absorbed. And if there are multiple different potential absorbances, then you'll get multiple different peaks. So you can see here, there's the presence of what seems to be two peaks. Here, there are clearly two peaks. There may even be another peak under here hiding, which affects the absorbances. They're generally pretty broad because unlike the lanthanides, these orbitals can be influenced by the outer orbitals or the ligands. So the ligands are kind of like, if we think back to the water around the small metal cations in our acid-base chemistry from previous courses, those water molecules which were coordinated or bonded to a central metal atom, those are called ligands. And those it's just a way of describing molecules or ions which are bonded directly to a metal center. It's just a way of describing them. I would call them ligands. And so the different ligands cause different effects on this energy. So we have here what it looks like for titanium. You can see it just really changes a lot. And so the position of these is always, of course, influenced by the chemical environment that they're in. And it really just sort of tells us a little bit about the color that we are seeing. So you have different peak absorption peaks at different wavelengths there. So here is what I was talking about, this change in the energy gap of the two, the HOMO and the LUMO. So if it's just a d metal atom, it has five degenerate orbitals. So we know that there are 5 d orbitals. However, oftentimes these d metal or like the d block metals, they're going to be bonded by some ligand, whether it be water, chloride, ammonia, whatever it happens to be. Here we've got some common ones here. And the effect that it has on the absorbance of chromium-3. So what happens is that the presence of these ligands with regards to how they interact with the d orbitals causes the energies to split. So instead of them being degenerate, they split. And so which ones split depends on what the structure is, but generally for an octahedral compound, and generally what you need to know is that they split the energies. The presence of the ligand splits the energy. How much the energy splits, i.e. what color we will see or what wavelength will be absorbed, changes based on the ligand. So the important thing to take away here is that the presence of ligands around D block metals causes a change in the energy levels. The changes in these energy levels affects obviously the energy of the HOMO and the LUMO. And depending on what ion or molecule is connected with the central metal ion, bonded to the central metal ion, will change this HOMO-LUMO gap. The changing of that energy of the HOMO-LUMO gap will cause a change in the wavelength which is absorbed. So the wavelength that is absorbed for a particular metal ion is going to be ligand dependent. So down here we see chromium 3+. So the metal ion does not change. What changes is the ligand which is bonded to the central metal. In the first instance, it is chloride, and we can see here that there is a wavelength of 736 nanometers. This means that it's going to be very low energy. It's going to have a very, very small energy gap because it's a longer wavelength. That's the lambda max for the complex. Water, then, you can see here, it shifts. Ammonia shifts. The diamine shifts. And then the cyanide. So the number here is 6 cyanides, 3 ene ligands, 6 ammonia ligands, 6 water molecules, 6 chloride ligands. And so you can see that we shift from visible through to like closer to UV, although still pretty much in the visible. There's a broad breakdown of ligands which cause visible and UV transitions. So like, for example, the halogens typically mean that the transition will be in the visible range of the spectrum. So usually you'll get colored compounds. As we move down towards things like ammonia and cyanide and so on, we move to higher energies, and we have what are called high field ligands, strong field ligands, and these cause UV transitions. This causes an increase in the energy required to, or the energy required to affect the absorbance, affect the excitation. And this obviously decreases the wavelength because lower wavelengths are higher in energy. Remember, that always goes back to Planck's relationship. Charge transfer absorption spectra. So these are a little bit different. So what's going on here is that there is some sort of combination of two species, whether they be molecules or ions or even atoms. And what they're able to do is that they're able to symbiotically or coexist and create what's called a charge transfer complex. And so this creates an electron donor group bonded or connected somehow with an electron acceptor. It doesn't need to be covalently bonded or something like that. It can even just be a very loose association in solution. But what happens is that there's some electron donor which can be bonded or in some way very loosely, or like even just van der Waals interactions are enough. And that means that the electron can bounce from the donor to the acceptor. And this causes, again, an absorption of radiation. This absorption of radiation can be very strong. You see here over here, this iron thiocyanate complex, this iron phenanthroline complex, and this starch iodine complex. They all have very high molar absorptivities. They're all very clearly visible. You can see here different ppm, we have different absorbances. So the large molar absorptivity here means that we have an epsilon max of larger than 10,000 usually, although the iron thiocyanate is a bit lower than that, but still clearly visible. So what's happening here is that the combination of the iron here with the phenanthroline, or the iron with the thiocyanate anion here, is causing they have an electron donor here, which is the thiocyanate anion, and it is donating electrons to the iron, which is what the absorption is. So it's no longer the HOMO and the LUMO are now in different species, but it's possible because of the specific energies involved. And so this is really actually quite a common thing. And there are many different organic and inorganic complexes which are capable of this. And if we look at the bottom here, starch is something we find in food. Iodine is an inorganic. So this is an organic, inorganic. This is an organic, inorganic. This is inorganic, inorganic. So this starch test maybe you've done before. Turns blue whenever it's in the presence of starch. That's the charge transfer complex. The starch obviously is colorless when it's on its own, but if you put it in position with iodine, then we have an electron donor and electron acceptor, and we see this bright, or well, it's a really, really dark blue. It just looks like black almost. So they've literally just dropped the iodine solution onto a piece of bread. Bread contains starch, and so that's why we have this strong absorbance of UV and visible light. So others, here's an organic example. So here we have what kind of like the energy of what's going on here. So we have an electron absorbance, which goes to the donor of the electron has an absorbance, which is excited to this donor. And then there's a transfer from the donor excited state to the excited state of the acceptor. And this is the charge transfer process. So the charge is transferred from the donor to the acceptor. And then this passes back down to the ground state of the donor, which is lower in energy. So it's kind of like a relaxation process, which happens via the acceptor down to the donor. And then light is emitted as part of this process. And so that's where we get the light. And usually this process might be lower in energy, and so it's more likely to be in the visible region of the spectrum. Say this could be in the UV spectrum, or it could be like in the IR where it's not actually visible, or not in the IR, it wouldn't be in the IR, but like it could be in the UV region, which is not visible. So this is just an ionic liquid. So here you've got this ring shape, this organic ring, which can be the acceptor of electrons from this methyl naphthalene. So you can see here the conjugated system. You could even calculate its absorbance maximum based on the Woodward-Fieser rules. And so this typically requires an electron donor and acceptor, and it can be intra or intermolecular. So the charge transfer can exist inside of the same molecule or between different molecules. Here we have different, or intra or interspecies. So it could be between this cation and this molecule. So that's definitely something which is possible. So measurement of UV. So UV spectrum, like for example, here for this triphenylphosphine, they usually lack fine structure, although this is one which has pretty good structure. You can clearly see a lambda max of 206 and 260. It's rare that you see literature reporting the full spectra. Usually they just report the lambda max in a particular solvent. So the report usually a numerical list of lambda max values or lambda max. So this is typically how you would see it in the literature. You wouldn't really see a spectrum like this. This is kind of a spectrum that you would obtain experimentally, but then you would report this as a set of lambda max values. So you would have a lambda max here and a lambda max here. So around about 260 nanometers and 206 nanometers. And so that leads us on to the next section, where we'll be talking a little bit more about the process of using these measurements and how we can utilize them in our instrumental and analytical chemistry.